On February 6, 2025, the highly sensitive detectors of LIGO and Virgo went into alarm mode and registered a telltale ripple in spacetime, which is nothing other than a potential gravitational wave, christened with the scientific name S250206dm. The detected signal suggests that something incredibly powerful must have occurred in the depths of the cosmos, but what that is precisely remains the exciting mystery that experts are currently trying to solve. But what exactly are gravitational waves? What can they tell us about the secrets of the universe? And why is their detection considered one of the most significant milestones in modern space research? In September 2015, the big moment arrived, and scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, proudly announced that they had detected the existence of gravitational waves for the very first time. In detail, the experts provided evidence of the phenomena that Albert Einstein had predicted 100 years earlier. However, if we look closely, the history of gravitational waves actually begins a little earlier, in the 1890s to be precise. At that time, the British mathematician and physicist Oliver Heaviside speculated that not only electromagnetic fields propagate in the form of waves but also gravity. This is because the force between two masses and the force between two electrical charges behave analogously when the distance between the two masses or charges changes. From a purely mathematical point of view, the two basic forces can therefore be described in a very similar way. And based on these relationships, scientists concluded that there could possibly be gravitational waves in addition to electromagnetic waves. A few years later, the Frenchman Henri Poincaré came to the conclusion that nothing can move faster than light, and this also applies to gravity, or rather to changes in a gravitational field. With this in mind, he suggested that gravitational waves originate from accelerated masses and propagate at the speed of light. Just like Heaviside, he also used electrical charges as a reference, which emit electromagnetic waves as soon as they are accelerated. Einstein's general theory of relativity was then to provide the solid basis for the prediction of gravitational waves. However, in contrast to his colleagues, Einstein did not regard gravity as a force but as a geometric property of spacetime, which consists of the three spatial dimensions and time as the fourth dimension. In this context, every mass deforms spacetime and thus also influences the orbits of other bodies. Although Einstein's name is still inevitably associated with gravitational waves to this day, it should be noted that he always showed a healthy dose of skepticism about them. After all, the tiny distortions of space-time caused by gravitational waves are probably much too small to ever be registered. However, other experts were much more optimistic in this regard, and in the 1950s, they succeeded in mathematically proving the existence of gravitational waves within the framework of the general theory of relativity. So far, so theoretical, but of course, it was still necessary to prove the existence of gravitational waves through experimental tests. To do this, scientists initially used large metal cylinders that were thought to be set in vibration by gravitational waves. However, this method did not ultimately achieve the hoped-for breakthrough, and indeed, it was still a long way off. The first significant intermediate step was achieved by U.S. physicists Russell Hulse and Joseph Taylor in the mid-1970s when they detected two neutron stars orbiting each other and realized that the energy loss of the double system corresponded exactly to the energy that such a system would have to radiate in the form of gravitational waves according to the theory of relativity. Although the two researchers were later awarded the Nobel Prize in Physics for their significant discovery, it was only indirect proof. As mentioned, it would ultimately take until September 14, 2015, before the LIGO detectors in the United States picked up a telltale signal from the depths of the universe, finally providing the astronomical world with a long-awaited direct proof of the existence of gravitational waves. To be precise, the groundbreaking signal came from a binary system of two black holes with 29 and 36 solar masses, respectively, located about 1.3 billion light-years away. As the gravitational monsters approached each other in ever narrower orbits, they finally merged into a new, even more massive black hole, releasing powerful gravitational waves that have since been traveling through space at the speed of light, passing through the LIGO detectors on our blue home planet. But how do you detect such ripples in space-time in the first place? In the case of LIGO, what were once metal cylinders are now two devices consisting of two perpendicular 4-kilometer-long tubes through each of which a laser beam passes. At the end of the tubes, there are mirrors that reflect the light back to superimpose the two beams. If a gravitational wave passes by, it stretches one arm while compressing the other, which ultimately means that the distances traveled by the laser beams are thereby lengthened and shortened. The two light waves no longer oscillate in the same rhythm, which generates a characteristic signal and shows the experts that the spectacles that were postulated over 100 years ago are actually taking place out there. To ensure that this happens as often as possible in the future, there are now several gravitational wave detectors that work on the same principle as LIGO. In addition to the Virgo detector in Italy mentioned at the beginning, these also include Kagra in Japan, to detect gravitational waves on the ground or, in other words, directly in space. Researchers are hoping for the friendly support of LISA. However, this is not the first name of a renowned astrophysicist but the abbreviation of the Laser Interferometer Space Antenna mission, which comprises 3 satellites. These are to form an equilateral triangle in space and send laser beams back and forth between them, thus forming a laser interferometer with an arm length of 2.5 million kilometers, or 6.5 times the distance between the Earth and the Moon. In this context, we could gain completely new insights into the world of neutron star binary systems or black holes. However, before we get that far, we need to be patient. As things stand, LISA will not be launched until 2035 at the earliest. Why is the most recent gravitational wave event so extraordinary? Of course, the researchers won't just twiddle their thumbs and wait in the meantime. After all, they have been able to detect dozens of gravitational wave events with the help of terrestrial detectors since 2015. As a rule, these resulted from the collisions of 2 black holes, but collisions of black holes and neutron stars or of 2 neutron stars have also been responsible for them. Just how important such observations are for scientists is shown by another example from 2017. At that time, a signal was registered that originated from the merger of 2 neutron stars in a galaxy 130 million light-years away. In the course of this, experts detected gravitational waves and electromagnetic radiation from the same source at the same time for the first time. The data provided experts with a comprehensive insight into the primal spectacle that took place in the minutes before the collision and in the weeks that followed. Against this background, it probably comes as no surprise that the scientists were once again in a flurry of excitement when LIGO and Virgo kicked off a few weeks ago. First of all, it was up to the researchers to localize the origin of S250206DM more specifically. They used special sky maps like BASTOW and BILBY to weigh the probabilities. The really crucial phase of the search began with the search for the flash of light or, more precisely, with the search for the electromagnetic counterpart of the gravitational wave. Just as lightning and thunder always go hand in hand, astronomers hope to detect these 2 components in pairs. Why this is so important becomes clear when we consider that gravitational waves can tell us that something has happened out there, but the electromagnetic radiation can also reveal exactly what has happened. Unfortunately, however, the hunt for the flash of light has not yet produced a direct hit. But what could have caused the event? Was it 2 black holes merging, a mass monster swallowing a neutron star, or something even stranger? To settle this question, researchers use sophisticated algorithms matching the shape of the gravitational waves with templates of different types of collisions to find the best match. To illustrate, You could say that the experts are trying to identify a musical instrument based on its sound waves. But that's not all. Although the search for the electromagnetic counterpart is still ongoing, it seems that the event is also linked to another discovery. Specifically, 2 neutrinos were observed at the Ice Cube Observatory at the South Pole immediately after the gravitational wave event. According to the experts, the probability of this being a pure coincidence is only 0.1%. Let's be clear. A so-called multi-messenger event of gravitational waves and particles is nothing less than an astronomical sensation. If researchers were then to succeed in identifying a flash of light that is also linked to this discovery, it would even be the first known triple event in the history of multi-messenger astronomy. As exciting as this evidence would be, time is of the essence. Scientists will use the coming weeks and months to collect and thoroughly analyze all relevant data, and only then will we know what really happened during this mysterious event and how it affects the world of cosmic research. Until then, we'll be happy to explain to you how your click and subscribe button works. Just press the thumbs up and subscribe now to never miss a new video from us again. We'll see you soon.